Peter Bogdan, I know, does do them because I made sure he does. Okay, so let us just proceed with where we left off. Okay, so last time what I did was I started saying, okay, well, obviously this whole section, we're working with the homogeneous differential equation, x dot equals ax, all right, so that's the one we want to work with. So far we've handled the real valued ones, except for the case where it's got repeated roots. That's got special things. So if you've got two real roots, then we know we can write the general solution, x of t is equal to some c1, c1 e to the lambda 1 t plus a c2 c2 e to the lambda 2t. All right. So we get our two linearly independent solutions based on the two eigenvalues. And if they are distinct eigenvalues, we know we have distinct associated eigenvectors with them. That's why I'm not doing the case where you have the repeated eigenvalue. Because the repeated eigenvalue gives us more complications to that. And we'll talk about that soon enough. But now we'd like to handle the fact that, of course, our 2x2 matrix can have complex eigenvalues. And if we have a complex eigenvalue, it'll have it associated with a complex eigenvector. All right? So let's assume we have this lambda in the form mu plus I mu, a real part plus an imaginary part there. All right? Again, we are only handling the case, we're only looking at the case where A itself is real. And we're only going to be looking for real solutions. Okay? So that's one of the things we have to do is how do we go from complex into real solutions? It's going to turn out to be a fairly easy way to do it, but again, it takes a little practice. So let's assume that this one, this differential equation has a lambda 1 equals mu plus I mu. Then it's not too hard to see that it's going to also have the complex conjugate will be an eigenvalue. So given that you've got, if it's an eigenvalue or eigenvalue complex, we get this eigenvector associated with that. And we can also see that what? If we've got the eigenvector for this one complex one, then the complex conjugate, we can pretty easily see the complex conjugate, the 2, it's going to have the conjugate vector there. Right? So once we've got one eigenvalue and its eigenvector, we've got the other eigenvalue and its eigenvector, trivially. Okay, so this gives us two complex solutions. So if we came over here, this would also hold, this particular thing over here would hold for the complex case if we're willing to accept complex solutions. Because what would happen, of course, is we would now have a complex xc here and a complex lambda here. And similarly, the conjugate, the complex one here and complex one there. These being two linearly independent solutions. But, of course, those are not real solutions. I will remind you again, so if I take e to the mu plus I nu t, this could be written as e to the mu t, and then using Euler's. Huh? So then this particular one will give us a cosine of nu t plus I sine of nu t. I like to use the Greek m and n, is what I'm using. That's the mu and the nu.
Yeah, I thought it was a v at first. So.
Nope, it's a nu. Okay. Two consecutive letters, m and n. Okay. So then that's just the Euler's formula. Okay, yeah, question.
The mu that's in the cosine is the same mu.
The nu, you mean the nu? Yes, those are the same nu. That's the frequency.
Got it. Thank
That's
you.
the frequency, and it comes back to the previous slide down here. This is the standard Euler's one. And last time I showed you, if you do the exponential expansion, the even terms gave the cosine, the odd terms gave you the sine. And so the natural Taylor series expansion of this gives rise to the natural Taylor series expansions of those. Okay? Again, that's what I've been sort of saying. You should remember exponential signs and cosines. And end of the semester, we will be doing power series. It's a technique of solving. Okay, so so if we look at my x1, there's my sort of my x1 over there. My eigenvector, there's my eigenvector here, a plus ib. We have the e to the mu t and the cosine ut plus I sine ut. All right?
What page is this?
So then we could look at the real part of this. The real will come from the a cosine
Complex
and the
eigenvalues.
ib I sine
Given the table of
gives us
contents, complex
this one.
eigenvalues.
Okay? Everybody, I squared gives us a negative, and so the real part of multiplying, this of course is a complex vector, this itself is a complex scalar. Right? And so we multiply those together, we get the real part here, the real part here, then the imaginary comes from the IB cosine, and the AI sine that. So what we see now is we've got from this x1, we've got this real part and this imaginary part. So we can split it up into the two pieces. All right. Now obviously, of course, we could get the x2. The only difference in the x2, of course, is we would get a minus here, and we would get a minus here. You would get basically the same thing, but you would get a minus there. Not exactly. There's a few other there's some other changes, but I don't want to worry about it. So we could write u of t being the real part, w of t being the imaginary part of this, and then that says what the x1 of t. x1 of t is just simply u of t plus minus. Oops. This one I'm trying to say that my x1 of t, I guess I didn't write that down. x1 of t is equal to this u of t plus I w of t. And we get the complex conjugate, we'll just get the minus there. Okay. Okay, so now let me, so there's my solution x1. Now remember, we have that x dot is equal to ax, all right? Now let me just change that to x dot minus ax is equal to 0, all right? Now again, A is a real matrix. Okay? So now this x dot, based on that x1 there, let me put some ones here. The x1 has to satisfy that equation. Then this x1 dot is going to be u dot plus I w dot, right? And then we're going to get minus A times this u plus I w, right? We could rearrange this and we could see this is going to be equal to u dot minus a u plus I times w dot minus a w, and that has to be equal to 0. Okay? Simple rearrangement. What does that then tell me? It tells me that u dot must equal AU, and W dot must equal AW. Because 0, this part is purely real, this part is purely complex. 0 would mean that it has to have 0 real part and 0 imaginary part, right? Necessarily. And so what this is saying is that this real part and this imaginary part, there it is up here, this real part and this imaginary part each satisfy the differential equation. So what that then suggests, and note that the u and the w are real valued, aren't they? Those are real valued functions. So then what that tells me is that I can now come down here and write my x of t is just another linear combination, and we'll use different coefficients here. We'll do a d, 1, I don't know, we'll do eta 1 u of t plus a d2 eta 2 w of t. And now that's all real value. And so we can take from, if we take the real and imaginary parts from our complex solution, we can then get a real solution with these two linearly independent solutions. I'm going to sort of quickly go through a little bit of more of the theory behind it. And by the way, you can also see what happens. If I were to add x1 and x2 and divide by 2, that's a linear combination of those, isn't it? Add them together and divide by 2, what do I get? I just get u, don't I? This plus this, divide by 2, is just u. If I take this minus this and divide by 2i, that is another linear combination. It's a complex linear combination. You're going to just get w, right? So you can see by taking linear combinations of these two complex solutions, I can get my two real solutions by doing the right linear combination. Okay. All right, so all this stuff is what I just got through doing. All right, so now how do we verify that these are linearly independent ones? We're going to use the Wronskian. Okay? I know you just love the Wronskian. Okay, so this is my u, the real solution. This is my imaginary solution based on what I had there. All right, so I'm going to put my real solution here. I'm going to put my imaginary part solution here, the u and the w. All right, that's just the determinant. Determinants are taken by multiply down this diagonal and subtract down this one. Okay, I'll let you go through the calculations if you want to, but there's a lot of sine cosines that cancel. There's a lot of cosine squared plus sine squareds, which go to 1, and it turns out that this reduces to this quantity. Okay? I'm not going to go through the details, but it can be easily shown. All right? So we got this particular quantity. Well, what did we need the Wronskian to be?
Non-zero.
It has to be non-zero. Do we know that this is non-zero? Well, we don't right off the top. Okay? We don't know right off the top that that's non-zero, but there's a powerful theorem that you should have gotten in linear algebra. I can't guarantee that you did. That if you've got two linearly independent eigenvectors, there's two linearly independent eigenvectors, because they can't be the two from the complex one and its conjugate. All right. So, what about these? Well, when you multiply them out, they equal that. But they were linearly independent because they came from these two distinct eigenvalues, right? Two distinct eigenvalues give you linearly independent eigenvectors. So here's the one from the the lambda 1, here's the one from the lambda 1 conjugate. You do the multiplication here. And again, you're going to get a lot of, you can see, for example, this A1, A2 is canceled out by this A1, A2. Similarly, you can see this B1, B2 is canceled out by this B1, B2. Those are all the real ones. Then you do the cross ones, they don't cancel out. They give you this. But by the theorem in linear algebra, you've got two linearly independent ones. They have to necessarily be non-zero. All right? So when is this non-zero? Well, it can only be non-zero if this quantity is non-zero. Look at this quantity. It's the same thing that appeared in the Wronskian, right? The exponential is never zero, right? So that's no problem. So this one, we had to show that this was non-zero, and we have, by the linear independence of solutions from linear algebra, big theorem, which you probably have forgotten, but that's okay. We just accept it. That theorem tells us that this has to be non-zero, so this is non-zero, the Wronskian is non-zero. That told us what? That real part and that imaginary part, real part and the imaginary part, those were linearly independent solutions. Okay? All right, that's the theory. Let's work an example. What's the nuts and bolts of doing this? Okay, I'll just erase this. So, I'll go ahead and put it up here. x1 dot x2 dot is equal to the matrix 3 minus 2, 4 minus 1, x1, x2. All right? The standard way we start doing this is we want to find the eigenvalues, right? We need to find the eigenvalues. So we're doing the determinant of 3 minus lambda minus 2, 4 minus 1 minus lambda. All right. See how well you can do on getting this. We obviously get lambda squared. All right. What's the cross term?
It's going to be minus 2 lambda plus 10.
Okay. Minus 2 lambda. Now we can see minus, so we get minus 3 plus, minus 3 plus 8.
Yeah.
Okay? All right. Let's do completing the square. Right?
Mm-hmm.
So what is my lambda equal to?
One plus or minus 2i.
1 plus or minus 2. Okay. All right. So now let's just go over here. So, for lambda 1, by the way, you're only going to have to take lambda 1, right? We don't have to worry about that conjugate because we're only going to take the real and imaginary. So we can just get the lambda 1, which again is this 1 plus 2i. So, what are we solving? This is the part that I know people have a little bit of difficulty with, is we're going to put into our matrix, we're going to get 3 minus lambda 1, all right? That gives us what? 2 minus 2i, right? So that first entry. Next entry, minus 2. We're going to get a 4. All right? What are we going to get down in the lower one?
Negative 2.
Minus 2.
5.
Plus 2i.
How about
Minus 2i.
All right? And we're trying to solve, let's just go ahead and put a v1, v2 here, equaling 0. Okay? Yes?
Why Why did you choose for lambda 1 to do the plus and not the minus?
Does it matter? It doesn't matter, does it?
It doesn't matter, the tradition is to take the plus. It turns out when you start getting into more complicated ones, like I do with 537, taking the plus makes it get into standard Jordan canonical form.
Got it.
All right. Though, quote, standard Jordan canonical form could be argued about. So it's just tradition to take the plus. All the calculations will work the same, and you're gonna get the same real and imaginary ones, are just gonna be off by a minus.
Okay.
Okay. So, what about this V1, V2? How about if I select the first one being 1? Suppose I select the first one being 1. What's V2 good?
1 minus I.
Yes. Right? And so you can clearly see this is 2 minus 2i. Put this in here, you're going to get minus 2 plus 2i. Let's give you 0. What happens here? If I multiply this, I get 4. What about this times this? 1 times this gives us a minus 2.
And the I
The I times this gives us another negative 2, right? 3 negatives in there. And the cross terms cross out, don't they? So we're going to get that 0 also. And it had to be, right? If it hadn't been 0, we wouldn't have had the eigenvalue. Okay, so I now have my eigenvalue and eigenvector. So I now need to write down my x1 of t. Okay, my x1 of t is going to be this 1 minus I, e to the, let me go ahead and write it in the complex form. It's going to be e to the t from this, and we're going to get times cosine 2t plus I sine 2t. And by the way, that's part of where, when you take the positive one, you get the plus I sine. If you take the negative, you get the negative of that. Right? And so that does have an effect on the Euler's formula.
Wait, can you say that again?
I'm just saying that by taking the plus, I get the plus here
Oh.
in the Euler's formula. All right? All right. So now, let me write this x1 of t. Okay. The real part. Okay? The real part is, so first of all, everything's multiplied by e to the t. Everybody agree? Everything's going to be multiplied by e to the t. Now, what are we going to get? The real part gives us what up here? Cosine 2t, right? How else do I get real part down? Well, so in the first one, for the first one, that's all I get. From the second one,
It's the I cancel out.
you can see that I get a cosine 2t. What else do I get for it?
Wouldn't it be times 1 minus
So I'm multiplying this times this.
I? Right.
So what's the other real part of it?
It would be that times the I sine 2.
So it's the minus I times the plus I, right?
Yeah.
Which will give us a plus sine 2t. All right. Then we're going to get plus I. All right. From that 1, I just get the sine 2t, right? Okay. Now, from here, do you see, we take the minus I times the cosine, will give us a minus cosine 2t, right?
Why aren't you putting I? Oh, I'm sorry, it's out.
The I's out front.
Yeah, sorry.
I'm breaking this down into the real component and the imaginary component, okay? And so then, the other one we get is the 1 times the I sine, right? So it will give me plus sine of 2t. And now you can see I basically got this into my u plus I w that I did in my general theory, right? And so coming back over here, erase this stuff, or I want to keep this stuff apart for some obvious reasons. We then can write the real general solution of my problem is x of t is going to be equal to some c1 e to the t times the real vector there, which is this cosine 2t, I can't see, cosine 2t plus sine t. Okay, that comes to the real solution. And then we'll get plus a c2 e to the t times this sine of 2t, and how did I write it there? I need it as minus cosine. Let me use this. That's why I need sine of 2t minus cosine of 2t. That's my linear combination of the real and the imaginary parts, right? Any questions on that? It's going to take you a little, I know for most of you it'll take a little bit of practice, but it wasn't that hard, was it? Just a little bit of complex arithmetic here. Some of the hardest parts, I can sort of remind you, some of the hardest parts is you gotta be careful, you always have to be careful to get the right eigenvector. So be careful, get the correct eigenvector. This is one of the things I hate most of all on tests, is students will mess up the very first part of the eigenvector. What do I get from then on? Garbage. It's really hard to grade garbage after step one. Okay, so be very careful, get good at getting these eigenvectors. Once you got the eigenvectors, you do this separating out. And then, well, we just take, this is one of them, that's the other one. Okay. Now what did we do, so what did we do last time? So what's the last thing I'm asking? We want to create. We've solved the problem. This is the solution. This is the real solution to this particular problem. We'd like a phase portrait. Okay, all of this is just, okay? So, what is the behavior of it? Sines and cosines are sort of cycling around, aren't they? The exponential is growing. So the result is you're going to get a spiral. As you will see in your homework problems, it'll ask, is it a counterclockwise one or is it a clockwise one? Okay. Now I'll give you what I consider the easiest way to figure this one out. I think I'll do it at the top so people can see it easily here. So I'm going to draw this phase portrait. x1, here's my x2. All right. So we know it's spiraling out, we just don't know whether it's spiraling out in clockwise or the counterclockwise direction. So now what I would like to do is, to show you this calculation, is suppose, so again the matrix up there, the A matrix, 3 minus 2, 4, minus 1. All right, suppose I take a vector sitting here at 1, 0. Okay? 1, 0, everybody agrees is sitting there on the x1 axis. Multiply times that matrix. What do I get here? What is that multiplication? So we're up top. 3, 4, right? Okay. 3, 4. Now, starting at this 1, I want an arrow pointing in that 3, 4 direction. It goes like that, doesn't it? So what that tells me is this has to be spiraling out in that counterclockwise direction, because it's from this point, it has to be entering the fourth quadrant, doesn't it? The flows are continuous on differential equations. So if it's coming across here, it has to, this is the direction field. We talked about direction field.
So it would be counterclockwise? Yeah.
And similarly, all other ones by continuity have to do the same thing.
Hope you can see that.
And so I find it's usually easiest because what? You've got your matrix there, you multiply by 1, 0, you just get that first column, right? And that first column will tell you, are you pointing into the first quadrant or down into the fourth quadrant? If it's pointing into the first quadrant, it's counterclockwise. If it's pointing down into the fourth quadrant, it's clockwise.
Is that enough for a phase portrait?
Yeah,
That's it?
yes.
Will it ever be pointing to the left?
Oh, this one could be, this arrow could be pointing this way, especially on a spiral end.
So if it's pointing this way, it's also counterclockwise?
So if it's pointing this direction, it's still counterclockwise because it's still crossing the x1 axis in the positive direction.
Okay, and if it's pointing to like the bottom left quadrant,
Pointing down there,
it's also, it's going clockwise.
it's going to go clockwise. So you're right, there's really only 4 possibilities. It's either going to point there, 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 or there. From that 1, 0 position. Okay. Now, it's kind of hard to draw these real accurately in the sense that exponential growth is fast. And so these things very rapidly leave the picture on this. Okay. But this sort of shows you the nice counterclockwise outward spiral.
So for our phase portraits on the exam, this is fine right here?
Yep, exactly. I will be looking for direction and whether it's pointing toward, coming in towards the origin or going out away from it.
Okay.
Is it spiral
Yes,
out
yeah.
or spiral in?
Are we
Is
gonna
it
do a
clockwise?
spiral in one?
No.
We're not?
You can handle that. It just
What does it look like though? Like, do we just point the arrows in? That's it?
Yeah, the spiral, so a spiral in the clockwise direction would just be the reverse of this.
Okay.
Okay. And obviously the spiral in is just one which has what? The exponential having a decay rather than a growth. So the only difference is the real part, whether it's plus or minus. Okay, so there we are. So this one's an unstable spiral, and it says if and this is so. Here's my full comment on my slides to what you were asking. If the solutions have a negative real part, it's a stable spiral. Okay. Let's move to another example. So we're looking at 2 minus 5 and 1 minus 2. All right? First of all, right away, is this going to be going clockwise or counterclockwise? It's going to go counterclockwise. Okay? Assuming we've got complex. Since we're working complex, actually I expect it to be complex. All right, so what we want to do is we want to get our characteristic equation. 2 minus lambda minus 5, 1 minus 2 minus lambda. That gives us lambda squared. What about the lambda term? 0, right? And so then what's left over? Minus 4 plus 5, how about plus 1? You okay with that? So, we've got lambda is equal to plus or minus 8. All right? Okay. So we'll just take the plus I. So we're now going to look at, we're looking at 2, so 4 lambda 1 equaling I. We're going to get 2 minus I. Okay, we're going to get minus 5. we're gonna get 1 minus 2 minus I. All right, call that V1 and V2 equaling 0. Okay. All right, so let's see, what could we choose here? Well, okay, I guess it doesn't matter too much. Suppose in this case we were to take 1 here, all right? Okay, then what would we have? We would have 2 minus I V1 minus 5 V2 must equal 0. All right, so we're going to have 5 V2 is equal to 2 minus I. So then we would get 2/5 minus I over 5. And so I would probably write this as the vector 5 over 2 minus I. Like that. Yeah.
Can you do a little more explaining of how we got all that? I mean, I get the 2RV1 minus big 5V2, but then how did you get the?
So then, solving this, if we take V1 to V1,
Okay,
because we can arbitrarily choose it.
yeah,
So choose it to be 1, then what must V2 be? It must be that. Right? That's a nice thing about solving these, in this two-dimensional ones. You can see if that's the one I used. Oh, I chose a different one. Yeah, I'll choose a different one. Not gonna matter. We'll work with this one, so it's gonna be different than the one that's in the notes. So, what are we gonna do with this? Well, let's write our complex solution based on, we'll use this eigenvector. And by the way, you can check that this would be an eigenvector for that. All right? So my x of t is going to be equal to, well, notice it's going to be this 5, the real part, the e to the mu t is of course 1, because there is 0 real part on this eigenvalue. So then multiplied times this cosine of t plus I sine t. All right. By the way, this is one of the challenging things on the exam, is each of you will come up with different eigenvectors, and I have to make sure each of yours are the right ones. So as you can see, the notes have one, this one has a different one. Okay, so I can then write this as, okay, we'll do the real vector. We're going to get 5 cosine t. All right, from the imaginary ones here, what we're going to get down here is minus a minus is going to be minus, so minus sine t there, right? Okay. Let me just put a C1 in front of that. Real part. The imaginary part, okay. What's the imaginary part? Well, it's going to be 5 sine t. And what's the imaginary? Whoops, I missed this one down here. Oops, my mistake. I'm trying to go too fast. I should get, down here, I should get 2 cosine t. And then the minus sine t. And then we'll get C2. The imaginary part is just going to be this 5 sine of t. Okay, imaginary part will give us a minus cosine of t. And we're going to get 2 plus 2 sine of t.
Where's the E?
Where's the I?
So that we get everything is multiplied e to the 0t. Right? Because the real part is 0. But e to the 0t is better known as 1. Okay? So it's just, all right. And one thing you can actually do is, of course, you can, if you take this real part and this one, if you take the right linear combination, you'll get the combination that I have there. Okay, so as you can see, you're not going to necessarily get identically the same thing each time. Because it really depends on what eigenvector you choose. You can get complex, well, you know, this one is 2i times that. Okay, so we've got my solution. All right, again, this one's different than this one. I'd have to do a little bit of manipulating to get it into this form, but I could. And then what happens on this one? We have 0 growth on it, right? The exponential is the 0t, so there's no growth. So this one is just going to create ellipses. And we already showed it had to go in the counterclockwise direction because that first, the 1 times that, goes 2 out this direction, 1 out this direction, basically the slope 2 coming out here. And then it just cycles around and does a nice elliptical path. Okay. So that's it for complex ones. And basically you have 3 possibilities with complex ones. You have this, which is called a center. That's where the real part is equal to 0. Okay? That says it's staying the same staying on elliptical orbits. Yes?
Well, how do we know what the number for e to the at is? How do we know e in that?
E to the
So,
at.
like the number you multiply t by after you put the exponent for e. How do you know what that is?
So we've got the Euler's formula that says e to the mu
right.
plus I nu, and if you multiply that by t, it's going to be e to the mu t cosine of nu t plus I sine of nu t. Right? That's Euler's formula. Okay, and so then we get, if the mu is equal to 0, we get what's called a center. This is also known as neutrally stable system. So it is a stable system because it doesn't go out, it doesn't come in. That's why it's neutrally stable. Paths of your planets go around elliptical orbits. Okay? Then we have the spiral in. That says that we've got a negative mu. Okay? And if it's a positive one, it's then spiraling out. It's a positive, with a positive mu. That's basically all we have. So we have spiral in, spiral out, center, and we have clockwise and counterclockwise. And that's basically it for the complex ones. So next time we will get into the repeater. By the way, looking at that one, can anybody tell me what the eigenvalues are? It's 2. It's 2. And look what happens if you take A minus lambda mu. What do you get? Get the 0 matrix. All right? So that tells you that you've got, for that eigenvalue 2, you have 2 linearly independent solutions, right? Because that's 0 matrix, you can take anything. You might as well take the coordinate axes. This is an easy one to do. But as soon as I put a 1 here, we only get dimension. By the way, if you put a 1 there, that is in Jordan canonical form. All right. So you might want to review your repeated eigenvalues and null spaces because we're going to go to the higher null space. Or higher eigenspace.